In this video, we will begin looking at how we can use the definition of the definite integral, the limit of this Riemann sum, to evaluate these definite integrals more analytically. So a few reminders here before we get going. So delta x, recall, is given by b minus a over n, and x sub I is equal to a plus I delta x. Now, when we evaluate using this definition, we have to end up taking a limit. And what we are going to be taking the limit of will typically be something that is rational in n. So maybe a simple example would be something like 2n squared plus 3n plus 100, all divided by 5n squared plus 1. And the big idea when you're evaluating a limit of this form, if it's as n goes to infinity, and it's a polynomial in n divided by a polynomial in n, if they have the same degree, the simple thing to know is that what you can do is take the coefficient of the n squared term in the top, we call it the leading coefficient, and the coefficient of the n squared term in the bottom. And the value of our limit is simply going to be 2/5. So take the leading coefficients and divide them. And this reminder will make evaluating the limits in the next few examples hopefully a bit more efficient. So let's use the definition of the definite integral to evaluate the integral from 0 to 2 of the quadratic x squared. Let me first remind you what it is we're calculating. If we sketch the graph y equals x squared, look at its graph from 0 to 2, it's entirely positive. So what we are trying to do is calculate this enclosed area. So I'm just going to call that A. So just keep in the back of your mind, we're going to lose sight of this geometric interpretation through the calculations, but that's the quantity that we really will be calculating. So the value of this definite integral is going to be just writing down the definition from the previous slides. The limit as n goes to infinity, the sum from I equals 1 to n, f of x sub I delta x. So in this case, let's go ahead and identify what each of these quantities is going to be. So our function f of x is x squared. We have a is equal to 0, b is equal to 2. Those are the limits of integration. Delta x is b minus a over n, so 2 over n. And x sub I is equal to a, so 0, plus I times delta x. So that's just 2i over n. So plugging this all in, we have the limit as n approaches infinity of the sum from I equals 1 to n, so f of x sub I. We're taking this x sub I, the 2i over n, and we're plugging that in for x. So that's going to be the quantity 2i over n squared. So this is corresponding exactly with the f of x sub I. And then we multiply that by delta x, so 2 over n. So the 2 over n is the delta x that we see above. And now what we need to do is, the limit and the sum, we're not going to calculate anything immediately with them, but we're going to keep writing them at every step. They're going to come along from the ride, and that means we're going to be using good mathematical notation. So we have the limit as n goes to infinity, the sum from I equals 1 to n, and let's just think out loud for a moment what we're dealing with here. We have 2 squared times 2. So that's going to give us a 2 cubed, which is 8. We have an n squared in the bottom times another n. So that would be an n cubed. And then we additionally have an I squared. So everything inside the summation simplifies down to 8 over n cubed I squared. And a very key observation is to note that we're summing from I equals 1 to n. So I is our index, anything that does not involve an I, say the 8 over n cubed, that's a constant, and we can pull that in front of our sum. So we can write this as the limit as n goes to infinity of 8 over n cubed times the sum from I equals 1 to n of I squared. And now what we're going to do is go back to one of our special sum formulas. And this is why those special sum formulas are so important. The sum from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1, all divided by 6. And what we now have to do is evaluate this resulting limit. So in order to evaluate this resulting limit, let's make it look just a touch simpler. We have an 8 over 6, which is a constant. We can pull that out front of a limit. Inside the limit, we have in the top, let's just go ahead and expand this all out. It will become 2n cubed plus 3n squared plus n. And in the bottom, we're dividing by n cubed. And notice what's going on. It's exactly one of these limits I hinted that we would be dealing with a moment ago. It's a limit as n goes to infinity, degree 3 over degree 3. So what we need to do is identify the coefficients of the n cubed term, 2 and 1. And the value of our limit is simply going to be those numbers divided by each other. So the value ends up in this case being 8/3. Now, as a reminder, because I know it's easy to get lost in what we've done here, we've actually calculated an enclosed area. It's the area enclosed underneath the curve of x squared between x equals 0 and x equals 2. In terms of how we go about this procedurally, we write out the definition of the definite integral, determine the quantities delta x, x sub I, so we can plug everything in, pull out any constants you can from the sum, and then the remaining sums we should be able to evaluate with our special sum formulas. And then the limit that remains, we can typically take care of it by thinking of it as a limit of a rational expression. So let's look at one more example of using the definition of the definite integral. Now, when I'm using the definition of the definite integral, the first thing that I like to do is to just write down exactly what that definition is. So the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x. And this shows me exactly what it is that I need to think about calculating, and it always gives me a starting point. So in this example, our function f of x is 2x plus 2. We're integrating from a equals minus 1 to b equals 1. Delta x is b minus a over n, so that would be 2 over n. And x sub I is equal to a plus I delta n. And what we need to do now is just plug all of this into our sum. So at each step, we keep writing the limit and the sum until we evaluate. That ensures that we have proper mathematical notation, and also helps to make sure that we don't make silly mistakes, which result typically from poor notation. So f of x sub I need to take the x sub I and plug it in for each x. So this would be a left parenthesis to get started, so 2 times my x sub I minus 1 plus 2i over n plus 2. So this quantity that we've written down is precisely the f of x sub I. Now I need to multiply it by delta x. So 2 over n. So the 2 over n corresponds to delta x. Now before getting too carried away, the first thing I'm going to do is just expand everything out inside the parentheses and then see if there's anything I can combine or simplify. So we have the limit as n goes to infinity, the sum from I equals 1 to n, and we have what? The 2 distributing through to each term. That will give us minus 2 plus 4i over n, and then the plus 2 that's there, times 2 over n. And this actually simplifies quite nicely. The minus 2 and the plus 2 go away, and we just need to take that resulting 2n and multiply it by the 4i over n. So this gives us the limit as n approaches infinity of the sum from I equals 1 to n of 8i over n squared. And just as we've seen in the previous example, we plug all this information in, we simplify as much as we can, and then we start pulling out constants. So this 8 over n squared is a constant with respect to I. So this is the limit as n approaches infinity of 8 over n squared, and I'm left with the sum from I equals 1 to n of I. And once we've pulled out constants, those remaining sums should be things we can evaluate with our special sum formula. So writing down our special sum formula, the sum from I equals 1 to n of I is n times n plus 1 over 2. And just going ahead and expanding everything as far as possible on the top and the bottom, we'll have 8n squared plus 8n over 2n squared. And once again, this is exactly one of those sums that I indicated we would see. It's an n going to infinity, degree 2 over degree 2. So we look at those leading coefficients, that is the coefficients of the n squared terms. 8 and 2, we divide those, and that is the value of our limit. So here we would end up having 4 as the value of our definite integral. Now once again, keep in mind, what does this number 4 mean? It does have a very nice geometric interpretation. For the function f of x equals 2x plus 2, it gives the net difference of areas enclosed from x equals minus 1 to x equals 1.